shapes of the orbitals are beyond what we expect you to know for this class. So don't worry about that. But what we do want to make sure you understand is that different orbitals have different energy levels. Some orbitals, it just takes more energy to be in. And electrons are going to, well, you can think of them as being lazy. They want to be in the lowest energy state possible. They're kind of, why run when you can walk? Why walk when you can sit? Why sit when you can lay down? Okay. So electrons want to be in the lowest energy state. And that's what we need to remember when we talk about electron configurations. Okay. So each one of these orbitals can hold two different electrons. And remember the order that we fill these orbitals in. So we do this. Now, for most of the things that we will work with, you won't go past 4. But if you want to be able to do all of them, then you have to go all the way down to 7. So next comes P, but there is no one quantum level P orbital. Okay. And then comes D, but there is not a 1 or a 2. Now, we could have a 7, but we don't have any atoms that have enough electrons to get to that level. And then finally we have F. So we start and we go make these diagonals. So the first one, 1s. Okay. For every s orbital, so all of these just have one orbital which holds 2 electrons. Okay. When we fill that one, then we go to this one. Then we get to a p orbital. Now remember, there's 3 different p orbitals, so that can hold a total of 6 electrons. Then, we get to S once again. Finally get to the d orbitals. There are 5. So that can hold a total of 10 electrons. And then we finally get to the f orbital. In the F, there are 7. So that can hold a total of 14 electrons. Okay. So the way we would do this, we would pick any element we want. Okay. Let's do sulfur. Okay. So we look at the periodic table and we see sulfur has the atomic number 16. So we're assuming that it's a neutral atom, so it also has 16 electrons. So we start right here, 1s. And remember, s can hold 2 electrons, so we put a little 2 right there. So we've used up 2. We have 14 that we need to put into the next orbitals. So we go to the next line. 2s. Once again, it can hold 2. So now we're down to 12 electrons that we need to do. We finish this line, so we go to the next one. 2p. That can hold 6 electrons. So now we have 6 left. 3s. That can hold 2 again. Then we come 3p. Now it can hold 6, but we've only got 4 left to put. So we put 4 right there. Okay. So that is the electron configuration for sulfur. Now we can shorten this a little bit. Remember, with our noble gas configuration. So if we look at sulfur on the periodic table, so if we go up 1 level and then all the way to the right, that is a noble gas. Okay? So everything in this very right column is a noble gas, except for oganesson, because that one is too radioactive to stick around. But what we can do, so if we go up 1 level and all the way to the right, we see that that noble gas is neon. Now the electron configuration for neon is 1s2, 2s2, 2p6. Okay. And if we look, it's the same as this. So we can write this as being neon 3s2, 3p4. That's the exact same thing. Okay. Now for sulfur, it's not a huge thing doing 16 electrons. But when you get to something like, I don't know, uranium that has 92, it gets a little annoying. Okay. So for uranium, what we would do, we go up 1 level and all the way over, and we get radon. Okay. Now, how do we know where to start after radon? Well, here's the nice thing. For reasons which will hopefully become apparent as we move through the class, you will always, after a noble gas, start with an S. So really, you just have to figure out what level it is. Okay? Now, for radon, that is in, you look at the periodic table, you can see there are numbers down the left-hand side. Radon is in the 6, which means we filled that. So the next one that we need to do is 7. Okay. Now radon, let's say we're doing uranium, so that has 92 electrons. Radon is going to take 86 of them. Okay. So if we have 92 minus 86, what does that give us?
12. No, just 4. 6.
6.
I am not.
Okay, so now we only have to do 6 more electrons. Isn't that nice? Okay. Instead of having to do all 92, we only have to do 6. So, how many electrons does the s orbital hold? 2, right?
Yes.
Okay. So we finished this line. What comes next? What is the next orbital? 6f. And we only have 4 electrons left. Okay. Now, to be 100% honest, that's not the accepted electron configuration. For this class, that's what I want you to do. Because once you get into these bigger ones, you have to learn some exceptions and things like that and some different rules. So just be aware, you go to college chemistry, that's not what they're going to want to see. Okay? Follow the rules that they give you. But for this class, that'll work. Okay? Everyone good with that? Okay.
So, Mr. White.
Yes.
So that one is E N or
This right here?
yeah.
That's an R, sorry.
Oh, sorry.
So yeah, with the really big ones, you do have to follow a little bit different set of rules, but we'll leave that for if you take chemistry in college. For this level, follow this, and we'll call that good. Okay. Now, the last, it's really interesting because on page 161, it's the last real page of content in this chapter, but it has two really, really important concepts: valence electrons and electron dot structures. So basically, valence electrons are sorry, I got distracted because I was looking at the real electron structure and something's off in this chart. Anyway, don't worry about it. Sorry, I'm trying to do college chemistry in my head while I'm teaching, and that doesn't work. So, anyway, valence electrons. Anything in this electron configuration past a noble gas configuration is considered a valence electron. It's the outermost electrons. Because what's happening, we have the lowest level of electrons, and they build on each other. Okay? Really, the further away from the nucleus, the higher the energy level, the higher the orbital. And so, valence electrons are the outermost. We've filled in all of the lower ones, and valence are what's left. Valence electrons are actually really, really important because valence electrons determine how something reacts. Determines how it reacts. And that is, like I said, this is a huge concept that it gives, a tiny little paragraph on. Now we're going to work with this concept over and over. This is just an introductory type thing. But yeah, the outermost electrons, the ones that if you write the electron configuration, anything past a noble gas, they determine how something reacts. Okay? Now, there is an easier way to determine how many valence electrons there are than writing the noble gas or writing the electron configuration. We'll get to it in a little bit though. So, because valence electrons are so important, we've come up with this way to depict how many valence electrons there are. And it's called electron dot structures. You may also sometimes hear me call them Lewis dot structures. Okay. So, same thing, just a different name. But what it is, we take the chemical symbol for whatever element we're dealing with, and we put dots around the outside to show how many valence electrons there are. Now, there is a chart on 161 that goes through from lithium to neon, and all of the electron dot structures. So we have lithium, and it puts a dot right there. So the question is, if you were to say that is the electron dot structure of lithium, would it be wrong? No.
Okay.
We care about how many dots there are more than where you put them. Okay? So, but lithium has one valence electron, so it gets put right there. Beryllium. Now the book puts them on either side. Typically when I do it, I actually would do it that way. That's just my personal preference. I don't care how you do it. Okay? But what you'll notice is, as we continue to go, then we get boron, and then we get carbon. So carbon has 4, and we've separated them out. Okay. Once we get more than 4 valence electrons, now we have to start pairing them up. Okay. It goes basically like we said with the orbitals. Okay. And how we said in the p orbitals, like if you were filling out the boxes, how you would do that, and then come back and do that. It's kind of the same thing. So after carbon, we get nitrogen, which has 5. And we get oxygen, which has 6. We get fluorine, which has 7. And finally, we get neon, which has 8. Now, as it turns out, 8 is kind of a magical number in chemistry. We will we'll really pound that into your brains. 8. 8 is a very magical number. It's what makes things happy. Anyway. So, now that we have done that review, let's move into Chapter 6. In Chapter 6, we are going to get into the periodic table. So you're going to learn how to use the periodic table a little bit better. Now, Section 1 goes into some of the history of how the periodic table was developed. I don't really care that you know that. It's interesting, but I'm more concerned that you know how to use our modern periodic table. So that's where we're going to jump. We're going to jump all the way to 177, talking about the modern periodic table. Now, when we talk about the periodic table, we have 2 major ways that we group things. Okay, so the vertical columns going up and down, those are called groups. A group of elements is everything in a vertical column. Okay? So if we were to look at, well, let's just look at group 1. Starts with hydrogen, and it goes to lithium, sodium, potassium, rubidium, cesium, and francium. They are all in group 1, up and down. Okay. Going horizontal the other direction, we call those periods. Okay. So period 3 has sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Okay. So up and down, groups. Horizontal, side to side, periods. So as you can see, we have 18 total groups and 7 total periods. Now, if you look at the periodic table in your book, you'll notice it breaks it down into several different categories. In the book, it breaks it down into metals, metalloids, nonmetals, and then it also has recently observed, although now we officially have them on the periodic table. Anyway, metals are really most of the periodic table. Most of the periodic table is classified as a metal. And then up here we have the nonmetals. Okay, right there along that black line is the metalloids. But we'll talk about these different groups. So, I do want to point out that several of our groups have specific names. And you've actually heard one of them that we've already talked about today, the noble gases. So group 18, they're called noble gases. Okay? The reason they're called noble gases is they don't react. They don't react very much at all. Can you force them to react? Yes. But just like the nobility would not have interacted with the peasants, the noble gases don't interact with other elements. Okay. So group 18 has a special name, noble gases. Group 17 right next to it also has a special name. It's called the halogens. If you've ever heard of a halogen light bulb, you may not have ever heard of that, and that's fine. But halogen lights are really, really bright, and they have actual halogen elements in them. So 17 and 18 on the right side of the periodic table have special names. There are two other groups that have special names. They're on the extreme left-hand side. So group 1 is called the alkali metals. In group 2, it's called the alkaline earth metals. So, all of these are then called transition metals. Okay. That's just the name they've given them. Now, I do want to point out these ones down here at the bottom. Okay. They're called the lanthanide series and the actinide series. They do actually belong in the periodic table. If you look right here, you'll see there's a spot for them. So why don't we put them right there? Because it would make the periodic table really wide. There would be a lot of dead space if we took this entire chunk here and stuck it right there where it belongs. So we just put it on the bottom and say, yep, that's where they go.
Okay.
So that's why it looks the way it does. You can actually buy a periodic table that has them in the right spot, but it's really wide. So we don't do that. So just so everyone's aware, they actually do go right there. So we got the metals, we got the nonmetals. Now, in this periodic table that I have on the wall, you see this thick black line right there.
Mm-hmm.
That represents where we find the metalloids. Okay. So everything that touches that black line except aluminum. But boron, silicon, germanium, arsenic, and everything else that touches that black line. It's what we call a metalloid. And it's actually really interesting because it's the boundary between metals and nonmetals. But those things that are touching that actually do have some properties of metals and some properties of nonmetals. So it really is, we've got the metals, we've got things that are sort of both, and then we have the nonmetals. So
How about the 57, 58?
these ones are all metals.
Oh,
Because remember, they go right here. And so everything on this side is metal except for hydrogen. Hydrogen is a nonmetal. It can behave like a metal under extreme circumstances, but that's the exception, not the usual. So. Okay. So now that we've had that introduction to sort of, the periodic table, let's kind of see how we can use it. Okay. First off, let's just kind of review what sort of information we find in each one of these boxes. Now, this periodic table on the wall has more information than the one in your book. So let's start with the one in your book. What kind of information do we see? Well, we have the chemical symbol. Everyone know what we mean when we say the chemical symbol?
Mm-hmm.
Yes, no?
Yep.
It's the 1 or 2 letter abbreviation. So for hydrogen, that's our chemical symbol. Okay. Pretty straightforward. Okay. We also find the atomic number. And what does the atomic number tell us? The what?
The number of an atom.
Not atoms.
Uh,
Protons.
Yep.
Yeah, the number of protons. So the atomic number for hydrogen is 1. So how many protons does it have?
1.
1. Very good. In your periodic table, it also has the full name written out. Now this is just, I'll point this out. It capitalizes all of the elements on your table. If you are writing them in a sentence, you don't need to capitalize them. Okay? Would I take points off if you did? No, because half the time I do anyway. It's just, yeah. But yeah, you don't, it's not a proper noun, you don't have to capitalize them. And then it has the atomic mass. Now the atomic mass is something that we will use quite a bit. You'll learn more about how to use it as we continue going through class. But remember, that's what we call weighted average of all the different isotopes. Okay. So hydrogen is normally just 1 proton, 1 electron, and then it's done. But you can throw in a neutron or 2 neutrons, and that does happen naturally. And so that's why the atomic weight is not exactly 1, but they're very rare. Most hydrogen is just the 1 proton. So I will also point out, the periodic table in your book lists the atomic weight, atomic mass I should say, as 1.008. If you look at the one on the wall, it lists it at 1.00795. Well, the one on the wall is actually more accurate. That being said, you can use the one in your book all the time. Okay. Our calculations, yeah, it might be a little bit different, but it'll be within a rounding error. So it's fine. You can use that one, or you can use that one. Doesn't matter. Just use whichever periodic table is available to you. Typically on your tests, I'll give you this periodic table. I have several laminated that I just keep, and so I'll hand them out so you can use them during a test. Because there's zero reason to memorize this. There are plenty of chemistry teachers out there that, for whatever reason, want their students to memorize the periodic table. I think that's a massive waste of time. Because I don't have it memorized. Now, there's a lot of information off of it that I do have memorized, just because I've used it so much. But to sit down, like, I couldn't sit down and go element 1 through 118 and just tell you all of them. It's a waste of time. So, okay. Now, I did say that the periodic table on my wall has a few extra things on it. So let's go over them. It actually has all of the electron configurations. Has all the electron configurations right there. So that's kind of cool. You can check to see if you're doing it right. It also, this one is going to have the freezing point and the boiling point. It's going to have the delta HF, which is something we will never use. It's the heat of fusion. It also has the delta HV, which is the heat of vaporization. Again, we'll never use that. The oxidation states, that is something that we actually will get into, but not for a little while. So don't worry that you have no idea what oxidation states means. Okay, we haven't gotten to that. And the density. And then the other side actually has some other information too, but yeah. So, that's just sort of basic. Can you look at it and read the words on it? So now let's talk about some other things that we can figure out once we learn a little more about the periodic table. Okay. So remember, I said that there was an easier way to determine the number of valence electrons than writing out the electron configuration. Periodic table tells us how many valence electrons something has. Okay? And it's actually super, super easy. So group 1 has 1 valence electron. Okay? Every single one of these things in group 1 has 1 valence electron. Isn't that nice? Group 2, who wants to guess? 2 valence electrons. Okay? Now, we are going to skip over these. We don't really deal with the transition metals and valence electrons, and honestly, metals and in the transition area with valence electrons, it's a little bit, metals give up their electrons really easily, so it's just kind of different. So we're just going to ignore them. We're going to move over to group 13. That's 3. 13 has 3. 14 has 4. 15 has 5. 16 has 6. 17 has 7. And 18 has 8. Isn't that so much nicer than writing the electron configuration? So, now we can look at this and say, okay, let's look at bromine. 35. How many valence electrons does bromine have? 7, because it's in group 17. Okay? So from now on, if you need to know how many valence electrons something has, Goes straight to the periodic table. What group is it in? It's that easy. Okay. So, we also mentioned like quantum levels when we were dealing with after a noble gas, what number do you start at? That corresponds to the period. So, anyway, we also are going to break the periodic table into different, what we call blocks. Okay? And we call these the S block, the P block, the D block, and the F block. Do those letters sound familiar?
Oh,
should.
Yeah.
Where do we find those letters?
The one thing we did on the board.
The one thing that we did on the board earlier, orbitals.
That's
Remember there's the S orbital, the P orbital, the D, and the F? Okay. So we can break them down into basically where we find the valence electrons. Okay. So S is groups 1 and 2. Group 1 and 2, the S block. Okay. Now technically helium belongs in the S block as well. The first period, well, you'll notice it's above the rest of the numbers because it's just a little bit different. We'll get to that. Okay. And then the P block is basically 13 through 17. Okay. D is 3 through 12 in this area. And then F are the two that get stuck down to the bottom. Okay. So basically, this tells us where we're going to find our valence electrons. Okay. Now once again, when we do valence electrons for this class, we're mostly going to focus on the S block and the P block. Like I said, you start to have a different set of rules when we get into the D and the F block, which you could learn, but we're just going to ignore them because that'll be one less thing for you to memorize. So, but anyway, I will point out, as you can see in the differences between the periodic table on my wall and the one in your book, the periodic table isn't finished. It's an ongoing process. Okay? Now this one on the wall is the most up-to-date version of the periodic table. It's the most up-to-date. It has all of the elements that the international, what's called IUPAC, it's the International Union for Physical and Applied Chemistry. I believe that's what it stands for. Anyway, they are the international governing body that determine whether or not we have evidence for a new element. Because everything with an atomic number greater than 92 was made by humans. We don't find anything greater than 92 occurring in nature. It just doesn't happen. So everything else is made in a lab, and if it was your lab, if you were in charge of it and you made this new element and have evidence that you were able to do it, you get to suggest a name for the new element. Now they do have some rules about naming. You can't just name it whatever weird thing you thought of. Can't name it element, element face, because that's just stupid. So we have some rules, but you get input. But what you should notice, there are no gaps in this periodic table. So the next time we successfully have a new element made, we actually are going to start a brand new period. We're going to start with period number 8. And that'll be interesting because for years and years and years, we've only been 1 through 7. Now we've known about period 7 elements for a long time. So it'll be pretty interesting once we get an 8th period. There is some evidence to suggest that, so most of these are really, really unstable and they fall apart almost as soon as you make them. There's some evidence to suggest that we might get to some more stable elements somewhere in the mid-120s, but we'll see. That is ongoing research. All right. So that's the end of section 2 in chapter 6. That's where we are going to stop for the day. And of course, because I know you love it, I have some homework for you. So, this will be at the end of chapter 6, and you can go ahead and get started on it. You got about 14 minutes.
Why is it always cold in here?
It matches my heart.
Okay. Okay.
Sorry.
Okay. That was a little deep. Now, also I'm upset because the hood in my jacket fell off in the wash. Not wash, just I don't know what.
All right. Once again, once the internet's working again, that'll be on